Okay, so backside. What'd you get for number 5A, Karen? Pardon? No, not the reactivity. Let's see here. That should be, if you're bombarding it with atoms in the vapor phase with a stream of electrons, that should be electron affinity. That's how they measure the electron affinity. So shoot electrons at it, see if, how much energy is released when they stick. How about 5B, Jared?
First ionization energy.
Letter C, worth?
Just like a bigger radius.
Bigger radius, that would be correct. They were looking for metal. But yeah, it's a little ambiguous. You're right, something with a big radius would be. So let's see, how about, what'd you get for 5D, Cassidy?
Increase?
Yep. So as you go across a row, ionization energies will increase. Let's see if I have it. What about E, Adam?
Decrease.
As you go down, it decreases. An element with a high ionization energy is classified usually as a nonmetal. The attraction an atom has for its outer electrons is called, oh, this is where I get messed up. Yeah, that one's electron affinity. This one is ionization energy. I get this messed up every year. Every year. An element with a low electron affinity is classified as a metal. Non-metals have high electron affinities. And now for number 6. They're asking you to explain the peaks. So in other words, they're trying to ask you, why does magnesium have a higher ionization energy than aluminum? If you look at the trend, here's magnesium, here's aluminum.
Sodium. Isn't it for sodium?
Between sodium and argon. They want an explanation of the peaks between sodium and argon. So the first peak is magnesium.
Oh.
So the question is, if I'm going this way, why doesn't aluminum have a higher ionization energy than magnesium? And the hint I gave you yesterday was to look at their configurations. Magnesium is neon 3s2. Aluminum is neon 3s2 3p1. So magnesium has a full sublevel. That's stable. But aluminum has a partially filled sublevel. Aluminum would like to get rid of that 3p. It would like to ionize. It would like to get rid of an electron. So the reason why magnesium has a higher ionization energy is because it has a full sublevel. So you have a fairly noticeable peak. Now what about phosphorus and sulfur, that other peak? Why is phosphorus having a higher ionization energy than sulfur? Well, once again, the answer lies in the electron configurations. Phosphorus has a half-filled P. Sulfur is partially filled. And then argon does follow the trend, but why does argon have the highest ionization energy of all of them between sodium and argon? Because argon is completely full. A completely full energy level. Is today Friday?
Yeah.
Okay. Monday we're in lab. Okay, so closed-toed shoes, hair tied back, or shave it off, your choice. Don't wear nice clothes that you're afraid that are going to get dirty. So we'll be in lab 2 days, Monday, Tuesday. It's a 2-day lab. Yep.
I don't think I'll be here Monday.
Okay. Then what you'll probably have to do is finish the lab sometime Wednesday. The lab really takes about a period and a half. So there's some extra time built in there. But you can't get the lab done in one period. It's too long of a lab. Okay, number 7. Oh, that's what we should do today. Demonstrations. We have some time. Underline the atom in each of the following pairs that has the lower first ionization energy. So the lower ionization energy. So lithium versus sodium. And again, I'm going to pick on everybody because we all have to learn this. So lithium versus sodium. First thing you always look at is electron configuration. All right? Lithium is ending in an S1. Sodium ends in an S1. That's a 2S1, that's a 3S1. So as far as configuration goes, they both have the same stability. So after configuration, Riley, then we look at atomic radius. Okay? So the bigger one will have the lower ionization energy. So who is bigger, lithium or sodium?
Sodium.
Sodium is bigger, so it will have the lower ionization energy. The reason is because it's bigger. Krypton versus rubidium. Well, krypton is a noble gas. It has got a completely full energy level. Rubidium, on the other hand, is krypton 5s1. So what's more stable? A full level or a partially filled level? Full level, right? So who's going to have the lower ionization energy, Emmy?
I'm sorry?
Which is more stable?
Krypton.
If krypton is more stable, it'll have the higher because it doesn't want to give up the electrons. It's kind of tough because, you know, they're asking for the lower. Cesium versus barium. All right, barium is 6s2, cesium is 6s1. So who has the more stable configuration, Kelly? Cesium or barium? Barium's got the more stable, therefore Cesium would have the lower ionization energy. Chlorine versus bromine. Chlorine ends in 3p5, bromine ends in 4p5. So again, always look at the configuration first, Brandon. Okay? They both have the same configurations, P5, P5. So then, Trevor, then you look at the size. Okay? Configuration first, and if they're tied, then you go on to radius. So who's got the bigger radius? Bromine or chlorine, Trevor?
Bromine.
Bromine has the bigger radius, so it's going to have the lower ionization energy. Fluorine versus neon. Neon's got a full level, whereas fluorine is ending in 2p5. What's more stable, Malky? A full level or 2p5?
2p5 chlorine.
Which one's more stable?
Oh, yeah.
Yeah. A full level's more stable. I think you jumped to the answer right away.
Yeah.
So that's the reason why fluorine is lower, because it is less stable. And then sulfur versus chlorine. Oh, this one's a tricky one. Tricky. Sulfur is 3p4. And chlorine's 3p5. So neither of them have a particularly stable configuration. It's not like we're comparing a full level to a partial level. Okay? They're both kind of equally in. So if you can't tell the answer from the configuration, look at the radius. Okay? Now sulfur and chlorine are right next to each other on the periodic table. There's sulfur, there's chlorine. Chlorine has one more proton than sulfur. Okay, chlorine's got one more proton than sulfur. So chlorine is going to be slightly smaller than the sulfur. Slightly smaller than the sulfur. So the smaller one is going to have the higher ionization energy. So the bigger one will have the lower ionization energy. That one I wouldn't give you on the test. That's a little too close. Okay, any questions on the homework? Yep.
Will there be problems like always on the test?
Yes. That's why I give it to you now, but it looks like we have to do some more problems. All right, so let's finish off the objectives today. We're going to talk about paramagnetic and diamagnetic.
When is the test? When is the test?
Test is next week, Wednesday. So take out your notebooks. I'm going to grab some fur and rubber. Okay, we're back. Sorry about those technical difficulties. So I like teaching paramagnetic and diamagnetic because it gives you an application of what we can use some of this stuff for. So first of all, we'll start with diamagnetic. Diamagnetic means you have no unpaired electrons. No unpaired electrons in those diamagnets. So here it would be helpful to know your Latin. Di in Latin means two. Okay? Bi in Greek means two. Okay? So if you ride a bicycle, Stephanie, you have two wheels, right? Bicycle. Okay? That's the Greeks. If you're from Italy, you're Latin, you ride a dicycle, right? Di means two. So diamagnetic means you have no unpaired electrons. So for example, magnesium. We're just going to look at the valence electrons. Magnesium is neon 3s2. All the electrons are paired. If you are diamagnetic, it means you are not magnetic. So magnesium is not a magnetic metal. Okay? So magnesium will not be attracted by magnets. Paramagnetic means at least one unpaired electron. And then you are magnetic. So people kind of get this messed up here, Sam, because they think paramagnetic. Okay, paramagnetic, you are unpaired. It's diamagnetic. Di meaning two is when you're paired. So let me give you an example here. Oxygen. Oxygen is 1s2, 2s2, 2p4. So you may look at this and go, oh, wait a minute, that can't be right. Everybody's paired up. I've got 2 electrons there, 2 electrons there, 4 electrons there. Everybody's paired. You cannot determine diamagnetic or paramagnetic from the electron configuration. You can only determine it from the orbital diagram. Yep, Garrett.
Does the amount of unpaired affect like the
Strength? Yeah. The more unpaired electrons, the more magnetic it is.
so like manganese or whatever would be a lot more magnetic than like sodium?
Manganese?
Yeah.
Yes.
It's 5.
Yes, it should be. If we do the orbital diagram for oxygen, and I'm just going to do the valence here. You have 2 unpaired electrons. So monatomic oxygen is magnetic, which means it should be attracted by a magnetic field. So I'm going to try to demonstrate this for you.